Out of all the objects in our solar system, none come close to the heat or energy output of the sun. In fact, within a single second, the sun produces 3.8 times 10 to the 26 joules of energy. That is 3.8 times 1 with 26 zeros, which is a big number. For comparison, here on Earth, we are using 5.8 times 10 to the 20 joules of energy each year. So, let's do some quick math. I know. Just stick with me. So our first number, 3.8 times 10 to the 26, comes out to this. It's a big number, so I'm going to put it on screen. And our second number, which is 5.8 times 10 to the 20, comes out to this. And I'll put them both on screen now together. With a bit of division, we learn that within a single second, the sun outputs roughly 655,000 times the energy that we use here on Earth in a year. So, yeah, that's a really big difference there, right? Because we're talking about a second of output from the sun and a year of consumption here on Earth. Take this energy and heat into account, and it comes as no surprise that the sun is incredibly difficult to approach, which makes it in some ways hard to study. For as much as we can learn from a distance, surely there's even more to be discovered by getting up close, right? This is exactly what the Parker Solar Probe has been doing, by helping us get closer than ever and study things such as the sun's corona, which is difficult to study otherwise. I actually did a video on the solar corona sometime last year, and I'll put a card up here somewhere for you to check it out, but it's pretty old, so be prepared for an even more scuffed version of Joe. We must still be careful and not get too close, though, lest, like Icarus, we lose our wings. So how close can the Parker Solar Probe get? In what ways are we protecting it, which allows it to do so? And what are some of the things it has accomplished and helped us learn about so far? These are just some of the things we will be going over here today. The concept that this probe was built on originates from the year 1958. A report was released by the Field and Particles Group, Committee 8, of the National Academy of Sciences Space Science Board. Within this report, several space missions were proposed, one of which was a solar probe that would pass inside the orbit of Mercury. For the longest time, however, there was a hurdle for solar probe missions, and that, as you may have guessed, was cost. Even with studies continuing through the 1970s and 1980s, had affirmed the importance of further studying the sun, it was not until the 1990s that a solar orbiter was planned as part of NASA's OPSP program. Even this program, however, would come to be canceled. Hey man, how's it going? Can you review the changes to this script for me, please? Wait, what? Dude, can't you see that I'm already recording? You can't just change the script now. Like, come on, man. You should have done that yesterday. What are you talking about? Come on, man. What are you talking about? Don't be like that. Listen, I'm sorry that it's a day late, okay? But, hey, I was a little busy yesterday. Sometimes we all got things to do. Oh, you were busy. Really now? Dude, you're the writer. All you do is write. Okay? What else could you possibly have been doing? Alright, really, man? Come on. Just take a look at these pages here, at this update, and let me know what you think. You know what? Fine. Yeah. Just give me that. Okay? Just let me see this. Hold on. What do we got here? Ridiculous. And from that moment forward, it was decreed that no probe shall ever orbit the sun. Well, there you have it, folks. Let's wrap it up here. I mean, I guess that's the end of the video. But seriously, like, really, you couldn't have told me sooner? Why did you have to wait until now? Crazy. Now, obviously, if that was really the case, it would be the end of the video, but we know that it's not. And so, enter the Parker Solar Probe, which at the start was simply known as the Solar Probe Mission. This project was announced in 2009 and would be part of that year's fiscal budget. But by 2010, this mission had been incorporated into a lower-cost mission that was known as Solar Probe Plus. These cost savings came from mission redesigns, such as multiple Venus flybys, which gave it a more direct flight path. This more direct flight path allowed the spacecraft to be powered by solar panels, rather than something like an RTG. And its new flight path also gave it a higher perihelion, which reduced the demands on the thermal protection system. Perihelion is the point where an orbiting body is the closest in its orbit to the Sun. The spacecraft was designed and built by the Johns Hopkins University Applied Physics Laboratory, and in 2017, the mission was named after Eugene Newman Parker, making this spacecraft the first from NASA to be named after a living person. And in the following year, on August 12th, 2018, the Parker Solar Probe was launched from Cape Canaveral Air Force Station in Florida. Following a successful launch, the probe was released from its launch fairing, being exposed to space for the first time. After separating from its second stage, the third stage fires, until it also separates from the probe. And with this, the probe is off to the races. After leaving Earth, it will perform the aforementioned flyby of Venus before inserting itself into an orbit around the Sun. An orbit that it has now completed 24 times, which have included 6 additional Venus flybys, each orbit bringing the probe slightly closer to the Sun. The Parker Solar Probe has achieved a lot of firsts, and it has helped us learn an unprecedented amount about our own Sun. Which by now, I'm sure you are either dying to hear or thinking, come on, Joe, get on with it. So, without further ado, let's get into the probe itself, what it has accomplished, and some of what it has taught us. Now, of course, we can't have a space probe without cool science instruments, can we? The first of which being SWEEP, or the Solar Wind Electrons, Alphas, and Protons Investigation. It has 2 complementary instruments that it uses to gather observations. The Solar Probe Cup, or SPC, which sits next to the heat shield, meaning it gets really hot, and the Solar Probe Analyzers, or SPAN. There are 2 SPAN instruments, A, which is looking ahead of the direction the spacecraft is going, and B, which is looking behind the spacecraft as it travels. What is done with these gathered observations? Well, the instruments count electrons, protons, and helium ions, which are the most abundant particles found in the solar wind. It measures properties such as velocity, density, energy, and temperature. This helps us better understand the solar wind and coronal plasma. Then we have WISPR, or the Wide Field Imager for Parker Solar Probe. This is the only imaging instrument aboard the spacecraft. It looks at the large-scale structures of both the corona and the solar wind before the spacecraft flies through it. WISPR takes images from afar of structures like coronal mass ejections, or CMEs, jets, and other ejecta coming off from the sun. All from an instrument that's about the size of a shoebox, so it's pretty small. These structures will eventually overtake the spacecraft, where instruments like SWEEP can take in situ measurements. Images from WISPR help scientists link what's happened in the large-scale coronal structure to the detailed physical measurements being captured directly in the near-Sun environment. The next instrument on our list is known as FIELDS, or Surveyor of Invisible Forces, or FIELDS if you will. The FIELDS instrument suite captures the scale and shape of electric and magnetic fields in the Sun's atmosphere. It does this by passing directly through said atmosphere. It has several sensors that help it gather data. 3 of them are located on the back of the spacecraft on a boom. This is known as the SCM, or Search Coil Magnetometer, and there's also 2 flux gate magnetometers, MAG-I and MAG-O, and these are all on the boom. Then there are 5 sensors on the front of the spacecraft up near the heat shield, known as voltage sensing electric antennas. Part of why we want to study these magnetic fields is because we believe they are tied to the heating of the sun's corona. Perhaps in some way, the magnetic fields are bringing that heat from another part of the sun, such as the photosphere, up into its atmosphere, or the corona. Now we have ISIS, which I'm going to put it on the screen. It's IS, a circle in the middle, and IS, but it's pronounced ISIS. It stands for the Integrated Science Investigation of the Sun. Something fun about its logo, which you can still see written out here, is the circle in the center is meant to represent the sun, what the probe is studying. This experiment looks at particles over a broad range of energy levels, spanning from around 10,000 electron volts to around 100 million electron volts. Let's take an electron for a moment and place it in a vacuum. Now, if we pass it through an electric potential difference of 1 volt, the electron will gain an amount of kinetic energy. This is the measurement of an electron volt. How will this instrument collect and study these particles? Well, the ISIS instrument has 2 different sensors, the Energetic Particle Instrument Low and the Energetic Particle Instrument High. And they are based on solid-state detectors. When a particle passes through them, we can measure both the deposited energy and the fact that the particle has really passed through the detector. Part of what ISIS is investigating is the difference between solar energetic particles that simply come from the sun with a certain amount of energy, and those that are energized in interplanetary space as they move outward and away from the sun. And this brings us to the thing that's really protecting it all, the heat shield. Known as TPS, or the Thermal Protection System, it is a composite structure made of top and bottom carbon-carbon phase sheets, separated by 4.5 inches of carbon foam that's between them. Between the back side of the heat shield and the rest of the spacecraft is a welded titanium truss that is about 4 feet tall. This minimizes the conduction between the heat shield and the spacecraft. On the front side of the heat shield, it is sprayed with a special white plasma optical coating. Like being in a white car on a hot day, this coating reflects a lot of the heat energy and light coming from the sun, helping to further cool the spacecraft. At its closest approach to the sun, the heat shield will reach a temperature of around 25 to 2600 degrees Fahrenheit. But the back side of the heat shield, just past that foam and the other plate, will rest closer to 600 degrees Fahrenheit. Then, beyond the truss, the spacecraft behind that is a nice, chilly 85 degrees Fahrenheit, so a standard operating temperature. Come on, where's this technology for our computers, right? That is some serious heat dissipation going on right there. And so, yeah, by now you might be thinking, well, that's great, Joe. We have a solar probe, and we have instruments powering its science, but you still haven't told us what it has actually accomplished. And, well, you know what? You would be right. So, let's get into some of that next, shall we? Just a few months after its launch in 2018, it became the closest human-made object to the sun. At this time, it was passing by at around 26 million miles. More recently, in 2024, it made its closest ever approach, coming within 3.8 million miles above the sun's surface. And we will come back to this one later. The probe is also moving incredibly fast, like really fast, with its top speed being around 430,000 miles per hour. This makes it, by a long shot, the fastest spacecraft ever built. Now let's talk about some of what it has learned, right? Starting with magnetic funnels. So yeah, it turns out, during its first set of flybys, the probe detected these strange flips or switchbacks in the magnetic field. By its sixth flyby, like by the end of it, it found that these flips were aligned with magnetic funnels found in the solar surface. Along the surface, there are structures called supergranules, which are basically giant bubbles. From these bubbles, hot plasma from the solar interior rises up, spreads out across the surface, cools, and sinks back down. Maybe kind of like a convection current. One of the biggest mysteries of the solar corona, which is the sun's atmosphere, is that it's like way hotter than the surface itself. This is kind of like walking away from a campfire, but it's getting hotter the further you get. There's a chance that these funnels hold the key to understanding why this is the case. Now, we touched earlier on the probe capturing energetic particles flying off the sun, and well, there are way more of them than we thought. Here on Earth, we rarely get any of these particles, which is probably a good thing, but the probe has picked up huge amounts of them around the sun. Just way more numerous than we had realized. And they come in many different types as well, often taking circuitous routes as they get captured by the flipping magnetic field. So they're not like orbiting in the most direct path that maybe you would expect them to. Jumping back to the corona itself, it appears to be wrinkly, so it's not shaped like a smooth ball. Instead, it contains valleys and spikes that wrinkle the surface. It seems this is tied to coronal streamers, which are giant plumes of solar material rising up through the sun's atmosphere. According to NASA, the results from these findings are reshaping what we know about the sun's atmosphere and how it transforms the solar wind. Even with all of this, though, I think it's important to mention that we do not fully understand the sun's corona and exactly how it's achieving the things that it is. On December 24th, 2024, the Parker Solar Probe would successfully make its closest ever flyby of the sun, which also broke the record for closest man-made object to the sun, right? Like the solar probe, it's just been breaking its own records for the last 7 years. This time, flying just 3.8 million miles above the sun's surface. Now, while that sounds far away in cosmic scales, man, it's nothing. For a comparison, the Earth itself is 91.467 million miles away. Now, if the solar system were scaled down to where this distance between the Earth and the Sun equaled a football field, the location of the Parker Solar Probe would be just 4 yards from the end zone, so way up near the end. Prior to this successful pass came the probe's final Venus flyby, which pushed it into its most optimal orbit. This orbit brings it to this closest point every 3 months, and the spacecraft will remain on this orbit for the remainder of its primary mission. As if it were to get any closer, I think even it would likely be destroyed by the sun, or you start really ramping up the risk of it taking damage, or just completely vaporizing. It really is a monumental feat to be able to get a spacecraft this close to the sun. This capability in a spacecraft took the space science community over 60 years to really tackle. The next planned close solar passes come on March 22nd of this year, 2025, and June 19th of this year, 2025. I believe, from what I found, that the pass in June will mark the end of its primary mission. Only time will tell if it continues studying beyond that. You know, for all of the mysteries we still have to discover in our vast, vast universe, I find it rather intriguing that there are still mysteries for us to solve here in our own cosmic neighborhood. There are a handful of scientific discoveries that I would love to be alive to witness, the official explanation and understanding of them. And one of them is definitely a full understanding of how our sun's corona works. On top of this, that would even help us to better understand other stars out there in the universe as well. While we may be near the end of this mission, I am still excited to see what more comes of it. And also in the future, and what kind of missions might come beyond the Parker Solar Probe. Now, have I missed something here? Or is there more discussion you would like to have? If so, please leave it in the comments below. I'd love to see you there. And if you liked this video, please give it a like and subscribe to my channel. And you know what? Who knows? Maybe even check out some of my other videos as well. With that, I would like to wish you a wonderful rest of your day. And of course, let us all step outside tonight and look towards the stars. Well, unless it's snowing, that is.